Alright, today we're going to continue doing increasing and decreasing functions, but we're going to do some different problems. We're going to actually be graphing or sketching the graph of f prime by looking at the graph that's given. So what we're going to do is we know that f prime is the slope of the tangent lines of the curve here. Well, if I talk about the slope of the tangent lines of the curve, notice how all the tangent lines to the curve have the same slope. So it's a constant slope, and the slope of the tangent line of the curve happens to be rise 2 and run 1. So the slope is 2 over 1. What that means is that at 0, the slope is 2. At x is 1, the slope of the tangent line is 2. At 2, the slope of the tangent line is 2, so on and so forth. So the graph of f prime would look like a horizontal line. The next example I have, a little bit more tricky. We need to look at the slopes of the tangent lines to the curve. What we're going to do first is, since it's not a constant slope, I'm going to look for places where the slope of the derivative is 0. So it looks like there's 3 spots. There's one here, there's one here, and there's one here. So there's one at -1. So at -1, the slope of the tangent line is 0. At 0, the slope of the tangent line is 0. And at 1, the slope of the tangent line is 0. Those give me some starting points to deal with. Now I have to start analyzing this graph. If I talk about slopes of the tangent line, look how rather steep and negative the slope of the tangent lines are. Then they get less and less steep negatively. So that occurs up to -1. So they start out really, really steep. So that means they're really like -4. And then they start slowly getting smaller and smaller, smaller. Again, this is just a sketch. It's nothing perfect. Then the slope of the tangent lines of the curve are all positive. They're all increasing. So that means they're all in this area right here until it hits 0 again. Right here, the slope of the tangent line is 0. But this is positive. It's all in the y positives. Then in this section, it's negative again. So the slope of the tangent line of the curve is negative. So I've got to come down here, and it's negative all the way to 1. And then the slope of the tangent lines to the curve for the rest of f are positive. And so a sketch that we could have for f prime would look something along those lines. Another example of these would be something along these lines. There is not a constant slope this time. There is nowhere where the derivative is equal to 0. So there's none of those horizontal lines, horizontal tangent lines. But something that stands out to me is this vertical tangent line. There's a vertical tangent line right there at that graph. What that means is that the derivative does not exist at 0. What happens on the rest of the graph? Well, these slopes of the tangent lines are really, really positive. Then they get less and less positive. Less and less positive. So they're really, really positive. Really, really high. Maybe this has a slope of 4 right here at 1/4. At 1/4 it has a slope of 4. And then it has maybe at 1 it has a slope of 1/2. Or maybe a little bit more than that. Just giving an idea that it's going to be getting smaller and smaller and smaller. That is the slope of the tangent lines of the curve. Going from the other side, these are also positive. We're going to finish up where I left off on this last problem, which when I was talking about the slope of the tangent lines for the right-hand side of this graph, and I had talked about how it was really steep and then less and less steep, so that's why we came up with that curve. Now on this side, we have a really not very steep tangent line. So at -4, maybe it's 1/8. Then at -3, maybe it's 1/4. Then maybe it's 1/2. And at -1, it's just getting closer and closer and more steep. So as you can see, if I was to draw tangent lines to the curve, they would get more and more steep. They would still never cross over that asymptote, and remember that asymptote occurred because of the tangent line to the curve right there is a vertical tangent line. The last example I want to talk about, the first question it asked me is to determine the speed of the ball bearing after t seconds. Now I want you guys to notice that you might think that there is some sort of product rule that's going to take place or whatever because this is a variable. But what we're going to be doing is putting constants in for each one of those. So we're just actually testing each one of the different speeds at a particular time. So we are not actually going to be using a product rule on this. We're just going to take the derivative, which gives me the velocity. That's 9.8 sine theta t. The speed of it is always the absolute value. So I've answered part A. Part B just asks you to complete the table and determine the value of theta that will produce that maximum speed at a particular time. So we don't even care how long we're going the speed or for how many seconds it's going to happen. We just want to know where the maximum speed occurs. When theta is what? So when theta is what sort of constant? What you're going to want is you're going to want your graphing calculator. You're going to want to be able to look at the table. That would be much easier to fill in this table with your graphing calculator. So if you don't have your graphing calculator, pause this, grab it, and then come back. You should have your graphing calculator by now. And what you're going to want to do is you're going to want to hit graph, the y equals button, and you're going to put in for y equals what s prime of t is. Remember, s prime of t is your velocity. So you're going to type in 9.8 sine x. Don't worry about the t. We're going to have t's in all our answers for our table. What we're going to do is we're going to ask the calculator at each one of these values, what is s prime of t? When I put in 0, I do get 0. I am missing that number. When I put in pi over 4, I get 6.92 t. When I put in pi over 3, and all I'm doing is asking my calculator each one of these things, I get 8.49 t. When I put in pi over 2, I get 9.8 t. When I put in 2 pi divided by 3, I get 8.49 t. And what you will find is this pattern where it's coming back down. So what we can determine from this table is that when or if theta is equal to pi over 2, the speed is the maximum. You can also, because it's increasing and then it starts decreasing, so it is a maximum. It's increasing and then it's decreasing.